By the end of the 19th century, the what of chemistry was pretty much falling into place. There were elements. The elements were different, had indivisible particles called atoms. The atoms had different weights. The atoms combined with one another in predictable fashion, like a 2-to-1 ratio or a 1-to-2 ratio or a 2-to-3 ratio or something like that. But it was really quite predictable. Mendeleev, a Russian chemist in 1869 actually, lined up the elements according to their weight and looking at their properties, realized that lining them by weight, there was patterns in their behavior. And in 1869, he came up with a periodic table, which pretty much stands to this day. But the whys, why did atoms behave the way they did, was completely unknown. By 1900, the structure of hydrogen was pretty well understood. It had a proton and an electron and nothing else, so it was the simplest element there is. Does the electron, how does the electron and the proton coexist? It's well known that the electron is attracted to the proton. So the electron goes around the proton, but somehow that didn't work under Newtonian physics. And furthermore, hydrogen, when it was heated up to a very high degree, would give off radiation at very specific frequencies. And none of this made any kind of sense at all. Niels Bohr, in 1913, he was a Danish scientist in his 20s, looked at this situation and said, instead of puzzling about why this happens, let's accept it for what it is and move forward. And he furthermore speculated that the electron was in a stable energy level in hydrogen and that there could well be other stable energies above that one, and maybe even many more stable energies. One of the premises that came out is that the electron doesn't behave like the moon going around the Earth. It rather behaves as kind of a wave function, so that the electron is actually in a wave as it goes around the proton. Take a look at this, if you would. It's free.
My name is Brian, and I play the cello. If I play the lowest note on the cello, a C, if I play halfway down the cello, it'll be a C, only an octave higher. If I touch, if I touch the string a quarter of the way down, it'll be a G. If I miss a little bit going halfway down, it will not make as good of a sound. As a cello player, I can change where I place my fingers on the cello.
So the moon goes around the Earth. The moon is gravitationally attracted to the Earth. The Earth is gravitationally attracted to the moon, so they're pulled toward each other. As the moon moves, there's centrifugal force pulling it away from the Earth. So you have the gravitational force attracting them, the centrifugal force pushing them away, and the result is a very stable situation between the moon and the Earth. So the proton and the electron have an electrostatic attraction to each other. So they're being pulled together. The electron is in a circular orbital. The electron moves around. There's centrifugal force pulling the electron away from the proton. No. There's no relationship whatsoever between the behavior of an electron going around a proton and the behavior of the moon going around the Earth. I know when I was a kid, intuitively, that seemed obvious to me, but that's not the case at all. The electron behaves as a wave as it goes around the proton. And there's certain constraints in how that wave has to behave. There's boundary conditions. Bohr called them orbitals. I like energy levels better, but orbitals in this case works better. The first orbital has two. The boundary conditions in this case is the circumference of the orbital. The boundary conditions put 2 electrons in the first orbital. And then there's a second orbital, and the boundary conditions are bigger. The radius is bigger, the circumference is bigger, quite a bit bigger, and there's 8 electrons that can fit into this. This boundary condition allows 8 electrons. This is a little bit of a deviation from what we're trying to promote here. I put this out because I think it's, basically because I think it's cool. Let's move forward. Hydrogen has, this is a common representation for energy levels, is you have E, and then the energy goes up this way. And then the hydrogen, the 2 electrons sit, or the 1 electron sits here. So the first energy level is here. This is a very simple graph. There's no x-axis. It's just there's just a y-axis on this one. The hydrogen is put like, a common approach is to put this like in a tube with nothing but hydrogen and subjected to very high voltage. If that happens, or if the hydrogen is put in like an acetylene flame or on the sun, this electron, the electron that's in the first energy level, will jump around and jump around and jump around, and pretty soon it will not be stable in that energy level anymore, and it will disappear and it will reappear at this energy level. So the electron will jump up to here, and when it does, it will absorb a certain amount of energy, not some amount. It will absorb an amount of energy equal to this amount right here. When it reaches that energy level, it will not be stable and it will fall down, releasing that exact same amount. And it will release it as a photon. And the photon will have a certain frequency. And a photon with a certain frequency is a thing much like this. It's a thing, and it's not going to do anything or change anything. It's not an arbitrary issue. The electron will move from here to here. It will absorb an exact amount of energy corresponding to this difference, and then it will release an exact amount of energy corresponding to that same difference. So the amount absorbed and the amount released is the same thing. And the energy, in this case, is released as a photon. The electron might get so excited, it might jump all the way up to this energy level. And if it does, it will absorb an exact amount of energy now corresponding to this amount. So this is a different energy level. And when it falls back down, which it will because it's not going to be stable up there, it will release an exact amount of energy like this, which will be a photon, and the photon will have a frequency associated with it. There are a bunch of energy levels up above, and an important and rather odd thing about this whole thing is that the energy levels exist even though there's no electron in them. So you have a proton with an electron in an energy level. The energy levels above it exist even though there's no electron in them. It isn't the electron doesn't define the energy level, which I think would be the obvious thing. Well, you put an energy in it, and the energy becomes the energy. No, the energy level is there anyway. So you heat this guy up enough, and you can get this guy to jump all the way up to the very, very, very high energy levels. And when they fall back down, you can find out exactly where those energy levels are by looking at the photons that are given off. I think it's cool. Chemistry, chemical behavior, in a very real way, fits everything in chemistry behavior fits this model. Everything, absolutely everything. Like like the wiggle of an organic molecule, or the color absorbance in an eye or in blue light or something like that, the color absorbance of anything, any kind of behavior, it may not give off a recognizable energy or absorb a recognizable energy, but there's an energy there because everything on a subatomic level is on a quantum level. It's a quantum deal. There's nothing happens except for on a quantum level. And there's going to be an energy change with every single one of those changes. As we move forward, we want to look more closely at the relationship between electromagnetic spectrum and molecular structure. This is mostly going to be done through examples. We want to take a look at why our visible light, which is so important to us and not a very big part of the electromagnetic spectrum, why is this particular part of the electromagnetic spectrum so important to us?